On this video, we will be discussing homework problems from section 4.1. In section 4.1, we work with one sample T procedures. So I'll begin by doing problem number one. I'm only going to do a couple of parts of problem number one. There's 4 parts here. But on problem number one, the idea here is for us to learn how to use the t-table. So the problem says there's 4 parts. Each part gives us a sample size. In part A, our sample size is 6. And our confidence level is 90%. And what are they trying to do? They're trying to help us learn how to use the t-distribution table that's in the back of our book. Now, the t-table, the first thing we need is our degrees of freedom. Remember, our degrees of freedom by definition is n minus 1. That's going to be 6 minus 1 or 5. So that's the row that we're going to use. We're going to use the row that says degrees of freedom is 5. Now, our confidence level is 90%. We have to interpret that. We have to translate that. What that means is if we were going to build a confidence interval, we would want the interior of our interval. We would want a 90% confidence interval. That means in each tail, because we have 10% left over, in each tail we would have 5%. Now that's important because that's how our table is organized. If we read across the top of our table, there's a row that says 1 tail. And right below it, there's another row that says 2 tails. Now we can read this from a 1-tail perspective or a 2-tail perspective. If we're doing the 1-tail perspective, we're looking for 0.05, 5%, 0.05. So when we read across, we have to find the 0.05 column. For 2 tails just means we're going to combine the 2 tails. We have a 90% confidence level. 10% would be the leftover in each in that case. So that would be not 0.0, that would be 0.05 plus 0.05. So that would be 0.10 would be the column. And it's the same column. Now what do? We read down until we get the intersection of 5 degrees of freedom and 0.05 for 1 tail or 0.1 for 2 tails. So if we do that and we read down, we get a t star value of 2.02. So our t star in that case is 2.02. So in problem 1, they're just helping us learn to use the t-distribution table. I'll do another part of problem 1. I'll do part C. Part C says n equals 29, and this time our confidence level is going to be 95%. Now, our degrees of freedom, remember, is always n minus 1, so that's going to be 29 minus 1, or 28. That's going to be our row that we're going to use on the table. So we're down here at 28 now. That's going to be our row. And we have a 95% confidence interval. So what does that look like? Well, that looks like the middle is 95%, 0.95 or 95%. That means we have 5% left over. So if we were using the 2 tails, we would be looking for 2 tails. 2 tails, we'd have 5%. We'd be looking for 0.05. In the 1 tail, right? In the 1 tail, there's going to be half of that. So that's going to be 2.5% or 0.025, which is the same column. It just however you want to think about it. Do you want to think about it as 2 tails or 1 tail? And if we read down in our t-table now we have 0.025 for 1 tail or 0.05 for 2 tails. We read down to the degrees of freedom is 28, and we get 2.05 for our critical t value. Our t star value for that example is 2.05. All right, so that's how we do problem number 1. So I'm going to erase this. and we'll look at a different problem. So our homework asks us to do problem number 1. It also asks to do problems 2, 3, 4, and 5. If we look at problem 2 just says we're going to work backwards here. It says we have a 90% confidence interval for a population mean. So we know our 90% confidence interval. In problem 2, we have a 90% confidence interval. And we know what that is, right? That 90% confidence interval goes from 65 to 77. They've told us the interval. The population distribution is approximately normal, and the population standard deviation is unknown. So since we don't know sigma, sigma is unknown, but our population is approximately normal, those are the key words to tell us that we're going to need to use the t distribution, right? Remember, the t distribution rears its ugly head when we don't know the population standard deviation. It goes on and it says this confidence interval is based on a simple random sample of 25 observations. So n is 25. Calculate the sample mean, the margin of error, and the standard deviation. They want us to find the sample mean, the margin of error, which is t star times s over the square root of n, and they want us to find the standard deviation, the sample standard deviation, which is s. These are the 3 things they want us to find. Now, to find these, we're going to have to use our knowledge of how a confidence interval works. Our confidence interval goes from 77 down to 65. The span of that from 65 to 77, that is 12 units. 12 units. Well, the mean is the midpoint of the confidence interval, right? We know that. We know the sample mean comes in the middle. X bar is right there. So we need the number that's halfway between 65 and 77. Well, a simple way to find that, right, would be go 77 plus 65 divided by 2. Find the average of the 2 numbers. That's one way to do it. 5 and 7 gives us 12. We carry the 1. That's 14, right? 6, that's, and 1 is 7 plus 7, that's 14. We get 142 over 2, or we get 71. So that's one way we could do it. We could say, okay, we'll find the average. Or we could think about the fact that this is 12 units long. That means it's 6 units over here, and it's 6 units over here. So if I move 6 units up from 65, I get to 71. If I move 6 units down from 77, I get to 71. So X bar is 71, whichever way you want to approach it. Now, we need the margin of error. Well, the margin of error is based on our definition of a confidence. Now, remember, our definition of a confidence interval is X bar plus or minus T star times S over the square root of N. This is, by definition, the margin of error. It's how far we go above and below the mean. Well, we can see right here, we go 6 above and 6 below. So our margin of error is going to be 6, right? That's the width of our confidence interval, or pardon me, half the width. It's the width from the mean to the end point of our confidence interval. Now they want us to find S. How are we going to find S? Well, we're going to use the formula that we have written right here. We're going to use this formula right here. And if we write that formula down over here, let me move this over here, we know that we have the formula right now, T star times S over the square root of N, but the square root of N is the square root of 25. That has to equal our margin of error, which is 6. Now, the square root of 25, the square root of 25 is 5. So now we have T star, we have S, we have 5, that's equal to 6. We can multiply both sides by 5, clear the fraction. And if we do that, we get T star times S equals, and we bring the 5 over here, 6 times 5 is 30. So S is equal to 30 divided by T star. Now, they didn't give us T star, but we can find T star. We know our confidence level is 90%. We know our sample size is 25. That means our degrees of freedom, right, is 25, n minus 1, 24. If we think about what it means to make a 90% confidence interval, we're back to problem number 1, aren't we? We have 10% in both tails, 10% in both tails, or 5% in a single tail, however we want to use the table, and our rho is going to be 24. So we look up here for 5% in one tail, or 10% in two tails. We want to go down to 24 as our degrees of freedom, and we get 1.71. So S is going to be equal to 30 divided by 1.71. And then we just grab a calculator, work that out, and we found S. So we can work backwards and forwards with confidence intervals. In problem 2, they wanted us to work backwards. Okay. So they also asked us to do problem 3. Problem 3 is very similar to problem 2, so I'm not going to work on that one. Then they asked us to do problem 4. Okay. Now, problem 4 is how to find a p-value with our t-table. We've talked about this in class. It's a little different, so I'm going to go ahead and clear the whiteboard here, and we'll go ahead and look at problem 4. Okay. Again, it's 4 parts. I'm not going to do all 4 parts. I'll do a couple of parts, though. And so problem 4 is, how do I find a p-value with my t-table, right? And I brought up a copy of the normal distribution table, because there's a big difference between when we use the normal distribution table and when we use the t-table. The p-value from the normal distribution table is in the body of the table. Okay, the p-value is these numbers here. That's our probabilities. That's the shaded region. However, instead of it being in the body of the table, with our t-table, the p-value is right here. This row at the top, this is our p-value. This is the only place we have to go to find the p-value. Whereas over here with the z-table, we can find an exact p-value. We cannot do that here, okay? So if you'll let me just real quickly, I know I've already had this on the board once, but we'll do it again. 1 tail, 2 tail. Our table goes 0.1, then 0.05, 0.025, 0.01, and 0.005. And then the 2 tail, of course, is just this times 2. So we get this, we get this. Here we get 0.02. Suddenly I can't multiply by 2. And here we get 0.1. Okay. These are the p-values right here. We're working with a different perspective than we were working with the previous table, the z-table. Okay, so let's take a look at how problem number 4 works out. Problem number 4 says we want to find the p-value, So if we look at problem 4, part A, problem 4 says we have an independent random sample selected from an approximately normal population with an unknown standard deviation. Again, those are the key words to tell us, right? To tell us that this is a t-procedures problem. So problem 4, part A says, they don't give us the null hypothesis because, to be perfectly frank with you, to do this problem, we don't need it. Now, the alternate hypothesis is that mu is greater than some value. And they don't tell us the value, they just tell us mu sub naught. So we don't know what the value is. We don't know. There's not a specific problem. This is just a general. So why did they tell us this? They told us so we know it's a one-tailed test. We know it's a one-tailed test because it's strictly greater than. So our rejection region, right? Our rejection region is this tail down here because it's greater than. So this is the tail that we are working with. It goes on and it says n is equal to 11. N is 11, which means our degrees of freedom, which again is n minus 1, is going to be 10. And our t value is 1.91. 1.91. It says in the problem, find the p-value for the given set of hypotheses and t-test statistic. Also determine if the null hypothesis would be rejected or not at the alpha equals 0.5 level. So this is our boundary to reject right here, right? This is our boundary to reject, the 0.5 level. Remember, we reject if our p-score is less than 0.05. So we're going to reject over here. And over here, we're going to fail to reject. And if I wouldn't label these on your t-table that you were given in class because we don't know. It may not be alpha equals 0.05 in the problem we're working on. But in this problem, problem 4, they told us our rejection region is alpha equals 0.05, right? So if we end up with a p-value in this area here, smaller than that, then we're going to reject. Now we need our t-table, right? We need our t-table, which I set over here. Here's our t-table. We're going to go down to the degrees of freedom is 10. 10 is here, right? 10 is here. And I'm going to go ahead and write that row on this whiteboard over here. So if we just imagine we went down to a degrees of freedom is 10. Starting on the left-hand side of our table, we have a value of 1.37. The next value is 1.81. Then we have 2.23. Then we have 2.76. And finally, our farthest value to the right is 3.17. Now, we've done an example like this in class, but we'll do one here as well. We take our t distribution value, right? Our t statistic came out at 1.91. 1.91 is bigger than 1.81, but smaller than 2.23. 1.91 falls right here. Right? It falls right here. What does that mean? Well, it means the area in our one tail is smaller than 0.05. If the area in our one tail was going to be 0.05, this number right here, this t-score, right, this t-value that goes along with that, the t-value that goes along with that is 1.81. Well, our t-value is 1.91, right? So our t-score is over here at 1.91. So we're in our rejection region. We're bigger than, our score, our t-score is bigger than 1.81, which means our alpha value, right, our probability, our p-value, pardon me, is smaller than our alpha value, which is 0.05. So our conclusion here would be to reject H naught. And remember what our H naught would be. Our H naught would be that mu is equal to some unknown value. So that's how we work backwards. We find where we fall between these numbers, And we use that to find our p-value at the top. So that was 4a. I'll go ahead and do 4b as well, or I'll do 4c. I'll do 4c. 4c is HA. And now we have mu is not equal to some value. In other words, we have a two-tailed test. All right. That's why I did 4C instead of 4B. 4B is also a one-tailed test. And then what are they giving us here? They've given us n is 7, which means our degrees of freedom is going to be 7 minus 1 or 6. And then they've told us our t statistic is 0.83. Now, we need a new row, right? This row here, these values here, those were the values for 10 degrees of freedom. We have a degrees of freedom of 6. So I'll go ahead and write those below here, even though in the real table they would be above, but this is the homework problem. So we'll write them here. I'm just looking them up. We have 1.44. We have 1.94. We have 2.45. We have 3.14. And then we have 3.71. And now we do the same exercise here that we did previously in part A. We take our t statistic and we try to find it. It's not between these. It's not between these because it's 0.83, right? It's not between these. It's not between these. In fact, it falls here. Now, we're doing a two-tailed test. So we're going to read the two-tailed row. Now, this, for a two-tailed test, right? This is a p-value of 0.2. We're to the left of that. So that means my pen is blowing up again. I'll just shake it until it all stops coming out. So that means our p-value, right? Our p-value is we're going this way. Remember, they get bigger as we go this direction. So our p-value is greater than 0.2. Well, so we are going to fail to reject. Sometimes our p-value that we get is not going to be between the values, but it might be at one extreme end. And all we can say then is that our p-value is bigger than whatever this number is. I'm again using the two-tailed row, not equal to two-tailed. All right. So that's how we do problem 4. I'll go ahead and do problem 6, and then we'll call it a day. Okay, for this video. Remember, I'm not trying to do every homework problem here. I'm just trying to do enough homework problems to answer any questions you might have, since you guys ask so many questions during class. Or the little sarcasm there, since you don't really ask any questions during class. Okay, so let's take a look at problem number 6. Okay, problem 6. Now, problem 6 is a problem where we actually have to do some work, right? And problem 6, the title of problem 6 is Fuel Efficiency of a Prius. Fueleconomy.gov, the U.S. official government source for fuel economy information, allows users to share gas mileage information on their vehicles. So you can go input your information on here because you may or may not believe what the dealer has to say. The histogram below shows the distribution of gas mileage in miles per gallon from 14 users. All right, so we're going to jot that down. N is equal to 14 here, which means our degrees of freedom, which again is n minus 1, is going to be 14 minus 1, or 13. Right? That's not a very big sample size. Remember, a lot of our decisions are based on a sample size of being greater than 30. Who drive a 2012 Toyota Prius. The sample mean, they tell us the sample mean is 53.3 miles per gallon. Okay. And the standard deviation is, so they know S is equal to 5.2 miles per gallon, right? They didn't give us the data, but they gave us the sample mean and the standard deviation, pardon me. Note that these data are user estimates, and since the source data cannot be verified, the accuracy of these estimates is not guaranteed. Okay, well, people called and told us this, so we're just going to go with it because we can't confirm it. They then give us a histogram, right? They give us a histogram. Remember, when we have a sample size of less than 30, we need independent observations and we need data that is nearly normal. That's what our little source of conditions say. So our conditions, right? Our conditions, because for every problem we do, we want to justify these. For our conditions, observations are independent. How do we know that? We don't want to just write observations are independent and then put a check mark. That's not college level work. We have to state why the observations are independent. We know that these are 14 users who submitted information to the fueleconomy.gov website. There's nothing about this to suggest to us that these are 14 people that drive, that belong to like a Toyota Prius club of Clovis or something like that. It just says there are 14 people that sent in information. So we would write a sentence here that says, based on the information given, it appears that these 14 data points are independent, since it does not state that these 14 individuals were related in any way. We need to write that out. Then we need to talk about, is this or is this not nearly normal? And then how do we do that, right? We got to talk about the shape of the distribution. I told you in class, I often like to just make a stem and leaf plot, but we don't have the data here. But they did give us a histogram. So you would want to say, based on the given histogram, the shape of the distribution is nearly normal. It's symmetric, it's unimodal, right? It's not skewed one way or the other. It's very close to normal. You have to write those words down. You don't write shape of distribution is okay and put a check mark. That's not, again, college level work. We have to have a conversation with the reader. So part A says, we would like to use these data to evaluate the average gas mileage of all 2012 Prius drivers. Do you think this is reasonable? Why or why not? Well, that's what we just talked about right here. Do we think it's reasonable? Well, our sample size is really small, right? We'd like it to be bigger than 30. It's way down at 14. That's not very big, but the observations are independent and the shape of the distribution is nearly normal based on the histogram that we've been given. So yes, I think this is reasonable. It goes on and says the EPA claims that for 2012 Priuses, they get 50 miles per gallon, city and highway combined. Do these data provide strong evidence against this estimate for drivers who participate on fueleconomy.gov? Note any assumptions you make as you proceed with the test. Well, the assumptions we're going to make, we'll note those as we go. So for part B, we need a null hypothesis. Our null hypothesis is that the mean is, for our group, the mean is going to be 50 miles per gallon. Sorry, I forgot the P in there. And then we have to be careful when we read the alternate hypothesis. It says the EPA claims that 2012 Priuses get 50 miles per gallon. Do these data provide strong evidence against this estimate? It doesn't give us a direction. It just says, does it provide evidence against this estimate? Do we think 50 is wrong? So our alternative hypothesis here is going to be not equal to 50. Now, we could argue that we only want to do a one-tailed test here. And the reason why is if our mileage is more than 50, we're probably not going to complain, right? If we tell you your car gets 14 miles per gallon and your car gets 20, you're not going to be upset about that. But if we tell you your car gets 14 miles per gallon and your car suddenly starts getting 6, now you're going to have an issue. So if we think about the way that this problem would work out, people aren't going to be too upset over here. If they're getting more than expected, right? If the mean is supposed to be 50 and they're getting more than that, they're probably not going to be too upset. Over here, they're going to be angry, right? Over here, they're going to be angry. But this problem is written so that we're going to do it as a two-tailed test. So now we have to do these data provide strong evidence against this estimate. I don't know, I haven't done the test, so I have to run the test. So I need my t statistic, right? Now t is equal to, remember, x bar minus mu naught, whatever they tell me that's going to be, divided by s over the square root of n. So here our x bar is 53.3 minus our proposed value of 50 divided by s, which is 5.2 divided by the square root of n. N here is 14. So that gives us 3.3 times the square root of 14, all divided by 5.2, just doing some algebra on the fly. I brought a calculator here. So my batteries are low. They recommend I change them. So I'm going to get 3.3 times the square root of 14 divided by 5.2, and we get a t statistic of 2.37. Now, how do we find? We need our p-value, right? Our p-value. And we're going to assume alpha is 0.05 here. We'll just make our standard assumption. They didn't give us an alpha value in the problem, so we'll just take 0.05. How do I find my p-value? Well, I'm going to get my t-table out, and we're going to do exactly what we just did in problem number 4. Our degrees of freedom are 13, so we're going to come down here to row 13. We have a value of 2.37. If we write the values down like we did in problem 4, you don't have to do this on every problem, but I'm just going to do it here again. I have for row 13, I have values of 1.35, 1.77, 2.16, 2.65. And finally 3.01. And I'm not going to write the header at the top. We know where these go. On a two-tailed test, this is a p-value. Well, we can just jot them down right here, right? For a two-tailed test, this is 0.2, this is 0.1, this is 0.05, this is 0.02, and this is 0.01. That's our p-values. And of course, I wrote them below here, but in the book and in the table, they're actually up above. So what do? We do the same thing we did in problem 4. We take most importantly here, we know that our p-value is less than 0.05. Since our p-value is less than 0.05, we're going to reject h naught, right? We're going to reject h naught. What does that mean? This provides strong evidence that we can expect that our average miles per gallon is not going to be 50 miles per gallon. And in fact, based on where we landed, right? We landed in this side of the table. Our estimate is that we're going to get more than 50 miles per gallon. So that's part B. Now, there's a part C to this problem, right? Part C says calculate a 95% confidence interval for the average gas mileage for the